So we are going to do some basic circuit solutions, and what we're going to do is we're going to do a series circuit, a parallel circuit, and a series parallel circuit. So first up we have a series circuit where we have one path for charge to flow. We have the positive side of the battery and the negative side. So we know that we're going to have a flow of positive charge out of the battery. The charge is going to flow through resistor 1, through resistor 2, and then finally through resistor 3. So as part of that, what we're going to do is we're going to worry about voltage, current, and resistance. And I'm not going to worry about power right now. So as we go through the circuit, we're just going to fill in information that we know. So voltage is the push, which is going to push the current through the wire through these three resistors. So the total current, the total voltage that we have is 36 volts. So we're going to go to the table and we're going to fill that in at 36 volts. So these are just the individual resistors, and this is voltage, current, and resistance, and I'm not going to worry about power right now. So the next thing we'll do is we'll fill in the resistances. So resistance 1 is 620 ohm, resistance 2 is 220 ohm, and resistor 3 is 100 ohm. So we'll quickly fill those in. Resistor 1 was 620. We'll write the ohms up here. We'll write the volt and the amp. We'll write our units in the headers. And 220 ohm and 100 ohm. So the first thing that we want to make sure we can do is replace all of these resistances, 1, 2, and 3, so we can solve this solution. What we'll have to do is we're going to have to go through and make what we call equivalent resistances. So basically what that means is what will we have to replace resistor 1, 2, and 3 with to be able to have the exact same current flow. So I'm going to call that equivalent resistance, REQ. And in series, equivalent resistance is equal to the sum of the independent resistances that the current must flow through. So resistor 1 plus resistor 2 plus resistor 3 is equal to 620 ohms plus 220 ohms plus 100 ohms. So as we go through that, we end up with 940 ohms. So again, just the actual sum of them. And that is only true in series. So we're going to write in 940 ohms. Now, once we have reduced this circuit, so basically what we have now is we have a battery of 36 volts, and we have one resistor. Again, there's my current leaving, and I have REQ. I can figure out the current because we know what Ohm's law says. So we can come back and we can do V equals IR. If we're solving for current, we're going to take voltage and divide it by resistance. So current total is equal to voltage total divided by the equivalent resistor, which again it would be this resistor that we just solved for. So 36 volts divided by 940 ohms, and that is equal to 0.0383 amperes. So we're just going to go through and we're going to solve this using a little bit of logic. Now, I have 0.0383 amps leaving the battery. So that means I must have 0.0383 amps returning to the battery. When the current leaves the battery on this circuit, it has nowhere to go except through all three resistors. So the current flowing through each resistor, so let's just label those I1, I2, and I3, they all have to be the same. So we can simplify that the total current is equal to the current going through resistor 1, which is equal to the current going through resistor 2, which is equal to the current going through resistor 3. So all three of those currents would be the same. So we can simply go down to our chart here, and we can just fill them all in, which will be the same. So it is the same current through this entire series circuit. Now, if you have current and resistance, then you automatically have voltage because you can just use Ohm's law to solve for that. So for example, let me do it over here. Voltage 1 is equal to current 1 times resistor 1. So that is equal to 0.0383 times 620 ohms. Voltage 1 is 23.7. Do the same thing here. Voltage 2 is equal to current 2 times resistor 2 is equal to 0.0383 times 220 ohms is equal to 8.4. And voltage 3 is equal to current 3 times resistor 3, and that's equal to 3.8. So that would be the series circuit solved. We know that, there'll be a little bit of rounding difference here, but we know that through the voltage rule, the sum of any closed loop will have to be equal to 0. So you send 36 volts out, you're going to lose 23 volts through resistor 1, 8.4 through resistor 2, and 3.8 through resistor 3, which will be approximately equal to 0 every time, which is the logic that we have to use to solve these circuits. And that would be the series circuit. So for circuit 2 that we have here, we have a parallel circuit. So we have a battery, once again, positive, negative, sending current out. And when the current gets to this particular branch, it can go down through resistor 1 or continue straight. Or go down through resistor 2 or continue straight. But when they get down here, they're going to start to come together. So the current in a parallel circuit is actually going to divide itself up. So once again, we're just going to fill in the information we have. We know that the battery is 24 volts. We know that resistor 1 is 470 ohms, and we know that resistor 2 is 2 kilo ohms. Write that in as 2,000 ohms. Finally, we know that the current going through this ammeter, or this particular branch, is 0.264 amps. So that would be going through resistor 3. Now, with this particular problem is we don't actually have two pieces of any of the information we need. So when we go to solve it, we're going to have to use a little bit of logic here. And we come back to that voltage rule. So the voltage rule says that if you currently is getting pushed with a force of, or a voltage of 24 volts, that 24 volts needs to be used up before it returns. In other words, 24 volts out, 24 volts being eaten up. If I were to hook a voltmeter across resistor 1, that is a closed loop. So I have to have 24 volts used up. I can also put my pen down and make a closed loop through resistor 2, and that would also have to equal 24 volts. And the same thing through resistor 3. So the voltage across each of these resistors would be equal to 24 volts. So in a parallel circuit, each closed loop needs to equal 24 volts. Now we have something we can deal with. We know the voltage and we know the resistance, so we can once again solve current. Remember our triangle. Voltage is equal to current times resistance. So we can start going to work. current 1 is equal to voltage 1 divided by resistor 1 is equal to 24 volts divided by 470 ohms is equal to 0.051 amperes. 0.051. So that would be coming down through here. 0.051 amps is down this branch. We can also solve resistor 2 for current because we have both voltage and resistance for it. So current 2 is equal to voltage 2 divided by resistor 2 is equal to 24 volts divided by 2000 ohms is equal to 0.012 amps. So coming down through here is 0.012 amps. Now, where we end up here, as I fill this into the table, 0.012 amps, is we know that when we're looking at this parallel circuit, the total current is going to be in existence here, but when it gets to this branch, it's going to start to split. So we know that the current going through 1, 2, and 3 have to add up to whatever we started with. If a river's flowing and it breaks into 3 streams, the water in those 3 streams should theoretically equal what we started with. So we can say current total is equal to current 1 plus current 2 plus current 3. Current total is equal to 0.051 amps plus 0.012 amps plus 0.264 amps. All 3 together. And I total is then equal to 0.327 amperes. And that makes sense. This resistor is 4 times higher than resistor 1, so we expect significantly less current through it. With most of the current going through resistor 3, it's a pretty good sign that that is going to be the smallest resistance because current will take the path of least resistance around. So when we get to this table that we have filled out, we now have 2 of the values for resistor 3, and we now have our total current, 0.327. I'm sporadically writing amps in. So now that we have these 2 values, we know that resistance, let's do resistor 3, resistance 3 is equal to voltage divided by current, voltage 3, current 3 is equal to 24 volts divided by 0.264 amps is equal to 90.9 ohms. And once you know the 3 resistors, you can then resolve them using the 1 over Req. So there's 2 things we can do. We can just solve using Ohm's law, or we can use the equation for resistance in parallel, which is just the inverse of the total resistance will be equal to the inverse of each individual resistor in the pathway. So, in the circuit. It is a lot easier and a lot simpler to say RT is equal to VT over IT. Just use Ohm's law. Then it's 24 volts divided by 0.327. And that's equal to 73.4 ohms. And that's how we can solve a parallel circuit. So next up, as we start to get to some of the more complex circuits. So this looks very similar to the circuit that we just did. It has 6 resistors, noticing the kilo ohms is there, and it has 1 battery. So the first thing we're going to do once again is we are just going to fill in the values. So we have a 24 volt battery, and we go through and we fill in the resistors. So 470 ohms, 2000 ohms, 91 ohms, 200 ohms, 150 ohms, and 33 ohms. And sometimes it's helpful to color code them. So for the first branch, I'm going to do them in green. Might not stand out well on the projector. The first branch, we'll do it in green. For the second branch, I'll pick pink. And for the third and final branch, I'll do it in orange. For no other reason except just to recognize that 1 and 2 aren't on the same branch and how it's actually set up. It'll be very helpful in this one to know what is connected to what. So we come back to our circuit, and I've just put a little line there to show the colors. And we have a positive side and a negative side on a terminal. We have current out and current back in. We know that the current out is going to be the total current. We know that that current is going to come up to this particular branch, this wire connection, and some of it will continue straight and some of it will go through the first branch. We know that the current going through resistor 1, because once that current starts down the branch, it's going to have to go through resistor 1 and resistor 4. So they're going to have the same current. So the first thing we're going to do is we're going to not deal with 6 independent current resistors. We're going to actually add them up. So what I want to do is I want to do REQ1, REQ2, and REQ3. So I have 3 resistors that are going to be basically imaginary resistors that we're going to put. And what we're going to do is we're going to collapse these 2 resistors into the single one. Now, resistor 1 and resistor 4 are in series with each other. So that means that to figure out the total resistance of this branch, which is what we're doing with REQ1, it would be equal to R1 plus R4. Because if it goes through 1, it's got to go through 4. That is series. So that would be equal to 470 ohms plus 200 ohms. So the total current going through branch 1 is 670 ohms. We're going to do exactly the same thing with REQ2. We know that REQ2 is going to be equal to R2 plus R5. Because if the current flows through R2, it's also going to have to go through R5. They are in series, so they just add up. So the total current, the total resistance through the second branch is 2,150. Finally, for REQ3, it's going to equal R3 plus R6, so 91 ohms plus 33 ohms. It's 124 ohms. So now I've basically done a circuit where I have a battery, draw out my battery, and I have 1 resistor, 2 resistors, 3 resistors, and I have REQ1, 2, and 3. So I have REQ1, 2, and 3. Looking at the circuit like this, it is exactly the same as the first one we did. We can actually solve the total resistance because now we have the resistors just in simple parallel. So I'm going to solve for 1 over RT, and that's going to be 1 over REQ1 plus 1 over REQ2 plus 1 over REQ3. That's equal to 1 over 670 plus 1 over 2150 plus 1 over 124. So 1 over RT is equal so 1 over 670 plus 1 over 2150 plus 1 divided 124 is equal to 0.010022. Now that is the inverse, so I'm just going to hit the inverse button on here, and I get RT is equal to 99.8 ohms. So we collapsed these together and got REQs and treated it like a parallel circuit, and then we just added them using the parallel resistance rule, and I got 99.8 ohms in total. See that being written in right here. Now the other thing that we know, and we'll just kind of fill these in as we go, but the other thing we know is we know that in this simplified circuit, that the voltage across each loop has to equal the total voltage. So as I get kicked out of the battery and go through the branch 1, I need to use, if this is 24 volt battery, then I got to use up 24 volts to go through this. So the current through branch 1 is going to be equal to the voltage divided by REQ1, or 24 volts divided by 670 ohms. So I1, or current going through branch 1, is going to be equal to 0.0358 amps. So I'm going to go over and just actually fill that in. Now remember, current branch 1 is made up of resistor 1 and resistor 4. So if that current is going through resistor 1, it's also going to go through resistor 4. So I'm going to scroll down to resistor 4 here and make sure it has the same number. I'm going to do exactly the same thing for current on branch 2. So I'm going to write I2 is equal to voltage divided by REQ2 is 24 volts divided by 2150. I2 is equal to 0.0111 amps. So that's going to have to go through resistor 1 and resistor 5. These are all amps. Amps, ohms, and volts. And finally, for resistor 3, or branch 3, current going through 3 is going to be equal to 24 volts divided by the total resistance of part 3. 24 divided by 124 will give me 0.194 amps. And that makes sense. It has the smallest equivalent resistance. It has the smallest equivalent resistance. Should be ohms. So therefore it would have the biggest current. So 0.194, 0.194. So now I have the entire circuit solved because I have 2 of absolutely every calculation. Now I know that the total current out has got to equal current 1 plus current going through resistor 2 plus current going through resistor 3. So 0.0358 plus 0.0111 plus 0.194 is equal to 0.241 amps. Similarly, we can also solve for that by going 24 divided by the total resistance using Ohm's law, and we get 2404. So we're off by 1/1000ths, but that's okay. Now for each of these calculations, voltage is equal to current times resistance. So we will go to solve for this one, we'll put current in, 0.0358 times 470 equals 16.83. We'll do it again. 22.2, 17.7, 7.16, 1.665, and 6.40. We don't have to worry about power. So finally, we're going to have a look at another complex circuit, series parallel circuit, with a slightly different configuration. We have 4 resistors and a 100-volt battery. So as we've always started, we're just going to start by filling in the values. So I have a 100-volt battery. Resistor 1 is 56 ohms. Resistor 2 is 120 ohms. Resistor 3 is 16 ohms. And resistor 4 is 91 ohms. So we start by looking at the circuit. We know that current is flowing out of the battery. All of the current that comes out of the battery will have to go through resistor 1. So resistor 1 is definitely in series. But then it gets to this point, and then the current can go one of two directions. It can go down through resistor 2, or it can go over through resistor 3 and 4 then. So resistor 3 and 4 are in series with each other. Resistor 2 and this branch are in parallel. So we're going to create a bunch of equivalent resistances, and hopefully that will help resolve our solution, resolve our circuit. So resistor 2 and 4 are together. So I'm going to start by writing Req1. So imagine I put an imaginary resistor here, or equivalent resistance here. It would be equal to R3 plus R4. So we'd add both of these up. So R3 is 16 ohms, R4 is 91 ohms. This would be 107 ohms. So now I have a circuit like this. I still have resistor 1, I still have resistor 2, but now I have Req1. And I know that that is equal to 107 ohms, which is exactly equivalent of resistor 3 and 4. I still have part series and part parallel, so I have to keep resolving. So we have to take this resistance, this circuit, and resolve these two branches together. So we'll still have a current, but we just want to replace both of those into one. And we're going to call this Req2. So 1 over Req2 is equal to 1 over R2, so that's 1 over Req1 is equal to 1 over 120 ohms, and then 1 over 107 ohms. So when we go through and do that, and we solve for the second equivalent resistance, 1 divided by 120 plus 1 divided by 107 is equal to 0.017679. This is 1 over R, 1 over R. So Req2 is equal to the inverse of that, to be 56.56 ohms. So 56.56 ohms. Finally, I have a circuit with two resistances, or resistors in series, so we add them up. I'm going to call this Req3, and Req3 is going to be equal to resistor 1, which everything had to go through anyway, and Req2. it's going to be equal to 112.56 ohms. And now that I have all of those resistances tied into one resistor, that's 112.56 ohms. Now we have voltage and resistance total. So current total is going to be equal to voltage divided by resistance is equal to 100 volts divided by 112.56. That's equal to 0.888. So we have 888 milliamps, or 0.888 amps, coming out of the battery. That current is going to flow up through resistor 1 and have to pass through resistor 1. So we know what that is. Nowhere else it can go. Now I can solve for voltage 1. Voltage 1 is equal to current 1 times resistor 1. .56 times 0.888. So the total voltage through resistor 1 would be 49.73. So if I were to take probes and measure the voltage across resistor 1, I would get 49.73 volts. So we have a lot of stuff solved, but we're still left with resistor 2, 3, and 4, where we only have one piece of information for. So this is where, once again, the voltage rule will come in and help us out. So resistor 2, if I were to take a voltmeter and hook it up across resistor 2, I would be able to figure out using the voltage rule, what the voltage across that would have to be. Because if 100 volts gets sent, is the force pushing out of the battery, and 49.53 volts is across resistor 1, then the voltage across resistor 2 would have to be whatever else is left from the 100. So voltage 2 is equal to 100 volts, take away 49.73, and let's just call that 50.3 volts. So 49.7 and 50.3 will give you 100 volts, and that's one complete loop has to equal 100 volts. So we come up to resistor 2 and we have 50.3 volts. Now, as we've been doing, current 2 is equal to voltage 2 over resistor 2 is equal to 50.3 volts divided by 120 ohms is 0.419 amps. So going back up to my circuit here, I know that I have a current of 0.419 amps going through branch 2. I know that I have 0.888 amps heading into this breakup, this connection. So the current that's going straight forward, let's call it current for resistor 3, has got to be equal to the total current minus whatever went down branch 2. And 0.419. That would be 0.469 amps. So through here, there must be 0.469 amps. That current's going to roll through resistor 3 and have to go through resistor 4 to get back to the battery. So the current going through resistor 3 and resistor 4 will be the same, and it will be 0.469. Finally, I know what voltage 3 should be. Just using Ohm's law, voltage is equal to current times resistance. I have two values. The voltage across resistor 3 is equal to 7.5 volts. And the voltage across 4 is going to be equal to current through 4 times resistor 4. It's equal to 0.469 times 91 ohms is equal to 42.69 volts. So we plug it in. 7.5 volts and 42 point, let's just call it 42.7. Again, you might end up with a little few rounding problems along the way, but generally this would be the solved circuit. All the boxes are filled out. I'm again ignoring power for right now.